Alright, it looks like we're live. Okay. So, yeah. Today is the last day of CMSC 201. So I'm going to pick up where we left off last time, and maybe we'll do some announcements first, because everybody loves announcements. So tomorrow's the study day, so that's the 13th. The final exam will come out the 14th, and it'll be due on the next Friday, so it'll be due on the 21st. And that's how it's going to work. It's going to be the same thing as it has been for all the other previous exams. Oh yeah, good point. There we are. So yeah, the final exam will come out the 14th. It'll be due the 21st. Anything else to say about that? There will be an MCQ section on Blackboard, probably. And I shouldn't say probably, definitely. And that's going to be it, right? Same stuff as always, right? And so I guess project 3 is due this Friday, so there will be a few days of overlap, and then basically I think that's almost it for the course. The only last thing to say is that make sure you at least try to do the new submit system test. It's worth 20 points, and it's basically free points. Okay? But they are 20 points. They're not extra credit, so not extra credit. So we replaced the academic integrity quiz because normally I give it before Project 1, and then I just kind of forgot to give it, and then it kind of lapsed. So it's pointless to give it now. If you haven't figured out not to cheat, then I don't think the quiz is going to tell you anything you don't know. Okay, so that's basically, I think those are all the real announcements that I wanted to go over today. I think that the rest of today I want to spend on, so my goal for the rest of the day is to go over the previous semester's final exam. And the reason for that is because it will be very similar to this semester's final exam. Most likely I will, my standard policy is copy the old one and then rewrite the problems, and that's what I do. And I use the old problems as kind of a hint to how to write, what problems to write. And that's how it goes. So let's look at the old final. It says spring 2021, but I did change that. That's the only thing that I've... Oh wait, so maybe we won't look at this one because this one's the current final exam. Okay, we'll look at the old one. Let's do that. So let me pull up the old final exam. You might say, but wait, I want to see the current final exam. They're both identical. The only thing I've changed is that it says spring on it. But let's see. There we go. But I want to give you guys the link to the exam, and I don't want to give you... well, so I can't do the current final because I haven't written it yet. That's what I'm going to do tonight. So, okay, I think... Yeah, so I think if I just copy link, this should give you the link to the previous final. So, yeah, so this is, basically what you're about to see in terms of your current final is going to be, it's going to look identical, except this is going to say spring 2021. Most of this is going to be the same, except for the dates. It's going to be a Friday, not a Wednesday, but you get the point, right? It's all just going to get changed. That's going to be, I'm not even going to modify this, it's going to be the same. Submission details, I'll just change the problem names, etc., etc. So let's go right to the first problem, because that's what you're really interested in, right? So problem 1 says, write a function called Jumble, right? And so what does Jumble do? You know, I have actually done that before in classes where I was teaching calculus once, and I wrote the answer to a quiz on a sideboard with some, not all, but some of the work, just to see when people walked in, like, do they look at the boards, do they, like, check out what's going on, and I don't think anyone actually looked. So, yeah. So, let's write this jumble function. So what does jumble do? It returns a jumbled string where the equation is defined, where we use, and so this is what caused a huge amount of confusion, where if you want index x, then I actually want index to jumble it. I'm going to take index ax plus b mod L, where L is the length of the string. And so, yeah, so basically how do we do this? So basically, let's look at this thing. So a string is equal to 9 words. And so for this example, and we set a equal to 3 and b equal to 7. So then 3 times 0 plus 7 is 7. So we count, we go 0, 1, 2, 3, 4, 5, 6, 7. We get d, and then we'll plug in 1. And so we get 10 mod 9, which is 1. So this is 0 and 1, so we get I. And then we get 0, 1, 2, 3, 4 for the next one. So we, this is 0, 1, 2, 3. I need to be careful with my counting. 4, so W is the fourth thing, right? So basically we see that if this is the index that we want, then this is the index that Jumble is going to give us, right? Using this equation, ax plus b mod L. And so then basically what we're going to do is output DIW. And the reason why we're going to do that is because I think I said don't reuse indices, right? So we'll only, but there's a twist. We don't want to use the same indices twice. Okay, that's the twist. Technically, if we were going to do this and it were just, so the simplest thing to do, so let's do, let's make some, what am I doing here? Let's call this final solutions. Okay. And so here what we're going to do is let's make simple jumble, right? And so for the simple jumble, all we have to do is just go for, say that, I in range len a string, right? We just go through the string, and then we would just plug it into the equation. We would just print out, or maybe we'd create an answer is equal to empty string. Answer is equal to plus equals a string at a times I, because maybe I'll just use x. This is x. A times x plus b mod length of a string. So this is, and then we can say, does it require you to print or return? I'd probably return, right? It will return the jumbled string. So we'll return the jumbled string too. So for instance here, if we print out like simple jumble on 9 words, and we do 3 and 7, which are A and B, what we're going to see is that we almost get the right answer. Except here we get DIW, 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 right? So this is going to give us like 80% of the right answer. Is just literally taking the formula that I gave you here and sticking the ax plus b mod L into the index and just doing that. So here, if a string is equal to a bunch of a's, right? Let's take this. A is equal to 5, b is equal to 0. The reason why that this returns a whole bunch of a's is because we're not allowed to use the same index, but you are allowed to get the same element. So because all the indices here are different, if you see we get 0, 5, 2, 7, 4, 1, 6, 3, the point is that all the indices are different, so we're going to be happy there. So let's do simple jumble on this string here, and we'll see what we get. And then we'll do it with 5 and 0. It actually doesn't really matter, but that, whatever. See, we'll get A's. And then finally, let's do this on A, B, C, D, E, F, G, H with the same thing. So, and I forget what we're, let's see what we're supposed to get. Hopefully we're supposed to get A, F, C, H, E, B, G, D. Let's see if that's what we get here. A, F, C, H, E, B, G, D. Good. Okay, but that's not exactly the right answer, right? That doesn't take care of the repetition business. So let's talk about, so how do we fix the repetition business, right? So here's the simplest and stupidest solution that I can come up with. Right? And so here's what I'm going to do. So let's say Jumble index is now going to be equal to this thing here. And then what I'm going to do is I'm going to say if Jumble index is in the index dictionary, well, if it's not in the index dictionary, what we'll do is we will add it to the string. Else, and well, no, there is no else. And then what we're going to do is we'll add, there we go. So now we see we've modified our initial solution, which is definitely a little bit simpler, but here we've modified our initial solution, and all we've done is just remembered the indices. Now you could use a list for this. The only reason why I use a dictionary and not a list is just because it's slightly faster in terms of performance, but again, we don't actually have to care about that because as you might guess, nothing here is going to really matter in terms of performance. So if we replace simple jumble with jumble, we're going to get the same answers for this one and this one. The only difference is here we're just going to get DIW. So let's get that. There we go. So that's problem number 1. And so what kind of tricks did I use here? So the tricks I used here was that first I jumbled up the indices with a formula, right? And that formula has to always mod by the length of the string, otherwise you're not going to get a reasonable, like if you get a number here that's beyond the length of the string, then you'll get an index error, so you always have to mod. I just made up a nice little linear equation that we could mod by the length of the string. The second part is like, how do we remember specific indices, right? And so how we remember specific indices is we remember things by sticking them into a list or a dictionary, right? That's really how we do it. Now you could make a class where you technically, or a class, but I'm not even going to say that. I'm going to say you remember things by sticking them into a list or a dictionary, and we check every time to make sure there's no repetition going on. Okay? That's it. So, and that's how we fix this problem. All right. So let me just put this into a def test jumble. Yeah, so if you were going to think about it recursively, the else is kind of like the base case. That's true. Yeah. That's if you're going to, but that's only if you're going to think about it recursively. Notice that there's no recursion going on here. So, I'm going to be a little bit nervous about saying the term base case, but yeah, other than that, I agree with you. Yeah. I get what you're saying, though. It does feel kind of like a base case, and you could theoretically do this recursively. Don't. So, let's go on to the next problem. I think these problems were... the fall semester, I think I made everything slightly too hard, so these problems are kind of challenging problems. So I think people got really confused on Jumble, and I kept adding more explanation and more explanation and more explanation. I'm not sure if it ever mattered in the end. But now that you see exactly what I want for Jumble, you're all like, well, obviously, that's exactly what the right answer would be, and how could anyone be confused about it? So let's look at this problem, which I think also caused some issues here and there. So longest string is going. Let's just copy paste this right into the into our code, and then we'll pass, and then okay, which takes a total string and a string called find string and determines the longest length of substring of find string. Oh god. Oh man, this problem is horrible. Now I remember why this one is terrible. So, yeah, this problem is, now that I look at this problem is probably too hard. But, whatever, let's do it. So, here's some examples. Let me zoom in a little bit so that we can all see what's going on here. So, you know, if I have in the grim darkness of the far future, right, there is only war. And so you see here that the longest part of this string that occurs is actually THE, and it occurs right here. So that's the longest substring of find string that occurs inside of here. And remember that a substring is contiguous. So you can't just mix and match letters. It's not just which letters occur. They have to occur in order, which is actually a good thing. Let's see. And then here, like for instance, 7 years ago, here we have wherefore art thou Romeo. You notice the ORE space A, that's the longest substring, and here is the longest substring, right? And so basically what you have to do is you have to search through all substrings of find string. So let me explain. This is an interesting, I guess this is an interesting problem. So how do you search through all substrings of a string? And the answer to that is, well, okay, what is a substring, right? You know, sub-question, what is a substring? And the answer to that question is, a substring is a contiguous string, a contiguous, I guess I was going to say substring. It's a contiguous sequence formed from the original string. And so basically the idea here is that if you have a string, say A, B, C, D, E, F, G, C, D, E, F is a substring, A, B is a substring, A, B, C, D is a substring, but A, E, F is not a substring, right? Because it's not contiguous. So here's the trick to think about substrings. Substrings have a start and they have an end, right? That's true about all substrings. And because it's contiguous, we'd say that substrings are parameterized by these two numbers, right? And so basically what we mean when we say that, and that's a tricky way of just saying, every substring has a start and an end, and it uniquely identifies that substring. So basically, any substring you can say, you know, for instance, so how do we list all the substrings of find string? Here's how we do it. We say for start in range len find string, right? And then for end in range len, I don't know, find string. But here we're going to start at start, right? And we can even start at like start plus 1, like that. Okay? And the reason is because what I'm about to do is I'm going to print out the find string, and this is not the answer to the actual problem. This is like listing all the different substrings. I'm just going to do this, okay? So now let's say longest substring, and it doesn't matter what we put in total string since I didn't use it. So let's print out all the substrings of A, B, C, D, E, F. There's going to be a lot of them, so let's print them all out. Here they are. So we have A, AB, ABC, ABCD, ABCDE, right? Oh, F isn't there, so we need to go to length plus 1. Remember, because the end part of a slice is always 1 after the thingy, so we have to go up to it. And we have to actually include the length because it's allowed to be in that parameter. Okay, let's run this again. There we go. That's about more right. So here we have A, AB, ABC, ABCD, all the way up to ABCDEF. Then we started B, BC, BCD, BCDE, BCDEF, etc. Right? And then we go C, CD, CDE, CDEF, etc. Okay, and those are all the substrings of ABCDEF. Those are all the substrings. Cool. And so, given that we know that, now all we need to do is just ask if that string, so find string, start, end, is in total string, right? And so remember what the in keyword means. The in keyword means that this little part is a substring of this, right? And if it is, then we say total length, and then we have to keep track of the max length. So we have max length equals 0. If max length is less than end minus start, then max length is equal to end minus start. Return max length. And that's it. So that's how to do it. You list out all the possible substrings, and then you use the in keyword. Now, if you couldn't use the in keyword, you would actually have to do 4 different for loops. You'd have to match the start with some position in the big string, right, and some end in the other, I'm actually sorry. You would need, no, I'm right. You would need 4 for loops. Basically, this is doing essentially 2 secret for loops for you inside of this in keyword, because it's trying to determine if this little substring is in here. So now let's look at some of the examples. So let's say, wherefore art thou Romeo? Let's put that in 4 scores and 7 years ago. So 4 score and 7 years ago. So let's print out the longest substring. 5. And if we remember, the answer was 5. Yep. So that's here's a more general example, right? This horrible sequence of letters. Let's copy paste it. And then this horrible sequence of letters is what we're going to look for. And so here we go. We're going to print out the longest substring of this, and we should get 3, right? Because FXW occurs right here, FXW. And so hopefully we'll get 3. Cool. So that's that, right? That's that. Okay. So, yeah, aren't these problems fun? I think that problem was, when I wrote that problem, it was less confusing. But now I think it might have been kind of confusing. I don't know. Maybe I'm just being hyper vigilant or something now. So, alright, so there's a poster that I always saw on, in the math building on the 4th floor at University of Maryland. And it was this thing where it says, if you add up the number of gifts on the 12th day of Christmas, you get some number. And the thing is that you remember that, like, on the first day of Christmas, you get the partridge in a pear tree, right? So you get 1 gift. And on the second day of Christmas, what do you get? You don't just get 2 gifts, you actually get 3 gifts, right? Because what do you get? You get, 2 turtle doves and a partridge in a pear tree, right? So the language of the song indicates that you don't get 2 gifts on the second day, you get 3 gifts. right? And then on the third day, what do you get? I forget all the things. Maybe I don't know the song well enough. Gotta look it up. So I don't say anything terribly stupid. You get 3 French hens, right? But you also get 2 turtle doves and a partridge in a pear tree. So you get 6 total items, right? And then on the 4th day, you get 4 birds of call, 4 calling birds. But then you get all the additional presents that you had on the previous day, right? So here's the thing. How many presents do you get per day? Well, there's this nice little chart which says, yeah, you end up with 12 partridges in a pear tree. That's right. So I guess I don't know if it's, I guess since they say partridge in a pear tree, you can stick all 12 partridges in the same pear tree. It's just you're getting 12 birds overall. Yes. So, so anyway, the point is that if you think about it, like how many gifts are you getting per day? The right answer is you're getting the index of the day plus the number of gifts that you got on the previous day, right? So what you're actually getting is n plus, like, g of, yes, but the birds come in a pear tree, but the point is that maybe it says a partridge in a pear tree, so it's possible that you could just stick all the partridges in this. It's almost Fibonacci. It's almost Fibonacci. It sounds Fibonacci. But what it really is, so basically the first day is 1. Cool. Right? The second day is 2 plus 1. The third day is what? 3 plus 2 plus 1, 6. The fourth day is 4 plus 3 plus 2 plus 1. And we're back to my favorite summation, right? The good news is that it's some kind of bird, but we don't have to care, right? Right, so this is the number of gifts per day. So I've given you a formula for the number of gifts per day. So the number of gifts per day is actually equal. So gifts per day on day D is equal to D times D plus 1 divided by 2. My favorite formula in CS, I guess, other than maybe Sterling. So this is the number of gifts per day. And so what does the actual question ask? Now we need to know what's the number of gifts total, right? What's the number of gifts total? And the answer to that question is, well, how many gifts do you get on day 1 plus 2? So it's 1 plus 3, you get 4. Then 1 plus 3 plus 6 is 10. 1 plus 3 plus 6 plus 10 is 20. 1 plus 3 plus 10 is 35, 1 plus 3 plus 6 plus 10 plus 15 plus 21, I guess, is 56, right? All of that plus 28 is 84, etc., right? Etc. So, let us write 2 different versions of this function. So here, you want to write a recursive function that does this. So, of course, and it says, your job is to write a recursive function that computes the number of gifts based on the number of days in Christmas, and so assume that Christmas can have any non-negative integer number of days. That's right, 364 total gifts. That's right. So let's make a NREC version, so a non-recursive version. The non-recursive version we could do like this. So we could say, what's the number of gifts per day? So we could say, for D in range day, right? And then here we could have we could do this. So for I in range D plus 1. So the only thing is we have to start at D plus 1, or we have to go up to D plus 1, because remember that if we're going to be adding these indices together, this is the easy, non-recursive, very pleasant version of this thing, right? And then we can return total gifts. And let's test this out, because maybe I'm totally wrong. Nth day of Christmas, day 12. So let's see if this works. If it doesn't work, then oops. Okay. Let's say def test longest. There we go. Let's run this thing. Cool. See, it printed out the right number. Alright, and based on this one test, we're convinced entirely that it works. Absolutely no doubt. Right, so let's say that Christmas had 365 days, then there would be, what? 8,171,255 gifts. Right? Nice. Is there an easier way than this? Yes, of course there is. Of course there is. The easiest way to do this is to use even more math. So basically here you can replace this for loop, because this is the Gauss sum. This is adding 1 plus 2 plus 3 plus all the way up to d, which we already know is equal to d times d plus 1 divided by 2. So we don't need this for loop. Actually, we can replace this for loop with gifts on day d is equal to d times d plus 1 divided by 2. And so this is the easier version of that. And so you'll ask, well, maybe there's an even easier way to do it. And the answer is yes. Because this is adding up. This is the sum of, from I equals 1 to n of, or let's say from d goes from 1 to n of d times d plus 1 over 2. And so basically, if you sum up d squareds, the sum of d squareds is equal to, and then we have the sum of d's, which is equal to d times, d plus 1 over 2. The sum of d squareds is equal to, what is it equal to? It's equal to d times d plus 1 times 2d plus 1 over 6. And unfortunately, there's a 1/2 sitting here, so we have to divide this by 12 and this by 4. And so the right answer, I think, in total, is that the total gifts are just equal to, day times day plus 1 times 2 times day plus 1 divided by 12, integer divided by 12, I guess, plus day times day plus 1. Oh wait, no, we can't integer divide. We have to regular divide, and then we can get rid of all of this, and we can just do that. So that's a 2-line function. In fact, we can just remove that variable and just return this. So that's the easiest way. And get rid of that variable. Now it's a 1-line function. So math will make us do this, right? Math is the easy way out. But you might say, but that's hard, because I don't know math. Okay, fine. Let's do it. So now let's do it recursively. So what you're allowed to do, actually, let's not even do that. Let's not even use the trick. Let's just calculate the number of gifts on day D, like this. And then what we can do is return gifts on day D plus nth day of Christmas, in this case recursively, on day minus 1. And of course here you're going to say, but wait, we don't have a base case. And so the answer to that is yes, we don't have a base case. So basically you say if day equals 0, or I'm just going to say if not day, turn 0. There we go. Now we have a base case. All right, that's it. So now let's test our recursive version out and see if it gives us the same numbers. Yep. So that's it. And so remember here that the reason, like, what are we doing here, right? We're calculating the number of gifts on the current day, and then we add that number to the number of gifts on all the previous days, which we calculate by just calling nth day of Christmas on day -1. And then, of course, here, if day is equal to 0, we return 0, because, you know, once you get to the 0th day of Christmas, we're not, you know, the song wasn't written by a programmer, so there's no 0th day of Christmas, right? Yeah. Anyway, so this is basically the answer, and I actually allowed, when they did the final, they were allowed to just do day times day plus 1 divided by 2, like this. So they didn't even need this for loop. They could have just, technically this function for them could have been 4 lines, right? So not bad, right? Not bad. It's a pretty simple recursion. The reason why I think it's a pretty simple recursion is because if you think about it, like at the end, what is this recursion really? So this is how you have to think about these problems. So what is this really? And the answer is, it's a recursive countdown. And we've done that all the time, right? That's how you compute Fibonacci recursively. That's how you compute factorial recursively. Nth day of Christmas is literally just computing. It's the exact same function. It's just instead of adding n or d or day or whatever, plus or d times factorial of d minus 1, or, you know, for some Gauss sum it could be d plus d minus factorial of d minus 1 or something like that. Here we're just adding this little calculation that we do with a for loop. That you don't even have to, so the point is you don't even have to do this calculation. I gave people this simplification so they wouldn't have to. Okay, so that's it. That's really it. Nth day of Christmas, right? So you see that here's the non-recursive version. Here's the easier one. Here's the easiest one, which I'm not 100% sure is correct, but yeah. Let's see if it's right. I'm just curious. I mean, maybe it's not right, but maybe it is. We'll see. It is. It just adds the decimal zeros because unfortunately it has to. You know what we can do? We can fix that. The reason why you can't just do integer division here is because this thingy is divisible by 6, and this thingy is divisible by 2. It's possible that a factor, because there's this extra 1/2 sitting here, that there's a factor of 1/2 that's going to be in both of them that will add up, and when those factors of 1/2 add up, you're actually going to see that they will give you another integer, which is why these are always point zeros, but the thing is, like, you can't just ignore it. Sadly, it would cause slight problems if you, like, integer divided and then rounded down and then, you know, because it would sometimes miss by 1. Which would be kind of confusing. Okay, so it's a fun problem, I think. That's a fun problem. So yeah, so the nth day of Christmas, pretty fun. See, I even wrote the formula. This is where I gave them the formula. I told them here. So let's check on the 821st day of Christmas, right? And we'll check on the 52nd day of Christmas just to make sure my numbers are right. Did I say 51st day, 821st day, or something like that? 23th, I think, maybe did I say 54th day? 52nd, 52. So, oops, okay. Hit insert, delete, end paren. All right. Yeah, 24,804, and what, 92 million, blah, 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 so, 24,804 and 92 million, blah, blah, blah. So, yep, we got it. We got it. All of them, all of our different calculations are essentially correct. If you're wondering where these formulas come from, the answer is that here is where they come from. They're all on this list of what are called Faulhaber formulas. So if you're looking up the sum of I to the 0, it's equal to n, and I of 1 is, you know, this, and then I squared is this, and I cubed is this, and I to the 4th is this, etc. As it turns out, there are formulas for adding up the powers of any set of, you know, or let's say, if you're adding up a polynomial, these formulas apply. There we go. That's the simplest way to say it, without saying too much, because now we're just going to move on. Okay. So, oh lord, starter code. Do I want to get the starter code? No, I don't even know if I'm logged into GL. Let me log into GL and see if I can get the starter code real quick. Yeah, so I required you to implement the... You know what? Let's come back to this problem if there's time. I feel like the other problems we can do much faster. So here's my version of a test to see if you can... So you can ignore most of this. Basically, the whole point here is we're going to convert numbers into base 7, right? So for this problem, we're going to use one of the luckiest and most useless numbers in computer science, 7, right? You must convert a non-negative integer to a base 7, to base 7, given that the number passed is an integer. Return the result as a string. This means no negative numbers are allowed, but 0 is allowed. A base 7 number is one such that digits are 0 to 6. A base 6, well, it depends what you're doing. If you're a number theorist, it's always better to be in a prime base. And if failing that, prime powers. So 6 is pretty bad because it's 2 times 3. And 2 and 3 are both, they're not the same prime, and they're... Anyway, so has a lot of issues. But, so basically 284 in decimal is 554 in base 7. And so the question is, well, how do you do that, right? And the answer is you do it the same way that you do all other things in the universe, is if you have 284, right, what do? You mod it by 7, and you get 4. Cool. And now you divide it by 4, or I guess you do 284 minus 4 divided by 7, so we get 40, right? So the first digit here is 4, and then what we're going to do is we're going to mod this by 7 again. So 40 mod 7 is 5, so that's why we get this middle digit of 5. And so then 40 minus 5, right, divided by 7 is 5. And then 5 mod 7 is just 5, so that's why we get 5, 5, and then 4, right? And so basically, it's the same exact process that you use to convert any other number, right? And so let's go through that process, right? Let's just make that process. So def lucky base, base 10 number, right? And so what we're going to do is we're going to say base 7 result equals empty string. And then we're going to say if the base 10 number is 0, we're just going to return the string 0, else, right? And so the reason why I'm doing this, you'll see why I'm doing this. We'll do while the base 10 number is not 0, right? And so this is why, because if I do this, unfortunately, it will cause an issue if the base 10 number is just 0. It's just going to jump over this loop, and it's not going to do anything. So what we're going to do is we're going to add base 7 result plus equals the string of, and this is actually going to produce the wrong answer, but it's the right answer, but backwards. So let me just do it this way, and then you'll understand why it's backwards, and then we'll flip it and do it correctly. So we're going to add that on, right? And then what we're going to do is we're going to take the base 10 number and integer divided by 7, right? Whoa, stop that. Divided equals 7. There we go. And so now what we're going to do here is then we can return base 7 result. And that's it. That's all you got to do. So let's def test nth day, and let's put all of this into a tabby thing, and then let's get all the numbers that we want to test. So here's all the numbers that we want to test. Okay. Yeah. So unfortunately, I think they're all kind of messed up. So let's see. What do we want to do? We want to test. Print lucky base on 0, and we want it to be 0, right? And then we want this one, and then this, and then this, and then this, and then this, and that's what we want to test. So this is our little chart. Okay. So we want to print lucky base of 5, lucky base of 15, lucky base of 381, lucky base of 2873, and remember that this is the decimal and then this is lucky, right? And then here we're going to do this larger number, and then hopefully once we run this program, right, so remember what I said. It's going to be correct, it's just going to be backwards. And so how do we fix this, right? So you see that it's 3501, whereas the right answer is 1053. This one is 34211. This one is 11243, right? So they're all correct but backwards, and so it's a little bit confusing looking. So why are they backwards? The answer is this line here, right? So this makes it backwards. And the reason why it's backwards is what it's doing is it's adding the new digit to the end. Whereas actually what we want to do is we want to add the new digit to the start. And so how do we do that? We do that by doing this. So unfortunately you can't use plus equals. You want to use plus equals because it feels right, but you have to do it this way because remember, plus equals is always going to add on like this, right, with the string at the end, but what you want is this, and there's no way to reproduce that with this plus equals, right? So this makes it backwards. This will be forwards, right? Because we're putting the new digit onto the front rather than the end. So now we're back. We're correct. So that's fine. That's good, right? Yep. Cool. So that's lucky base, right? Lucky base. So what's the point of lucky base, right? The point of lucky base is that what does the while loop exit when it reaches 0? Yeah, so remember what's happening. We're dividing the base 10 number by 7 each time. And so eventually that number is going to be 0. And remember what happens when you check, when I say while base 10 number, right? And that thing is an integer. So what is it going to do? It's going to loop through the loop until the base 10 number is quote unquote false. And then you remember, well, what does it mean for any number to be false, right? For a float or an int to be false? And the answer is they're false when they're 0. So this is true when it's non-zero. Basically, this is the same thing as writing while this thing is not equal to 0, like that, right? But most programmers will just write it like while base 10 number because they don't like putting in the not equals 0. It's strange in I'll call it like real code to see someone actually write that. Okay. So let's go and look at the next problem, right? Oh, 8 pickets. Oh god, 8 pickets. I love 8 pickets, but it's terrible, isn't it? So let me show you the first picture first. Here's the first picture. So a picket is not actually a chess piece, as anyone who knows chess well enough would probably tell you, but the King Tamerlane back in, I think, was it like the 1300s or something? Yeah, I mean, it is going to be similar, right? Like, these types of problems are always just shades and, shall we call it, variations on a theme, if you know what I mean. So a picket is like a modified bishop in something called Tamerlane chess. And so in Tamerlane chess, the picket cannot move a single space. So it can't go here, it can't go here, it can't go here, it can't go here. But it can go anywhere else that a regular bishop could go. So it can move diagonally, it just can't move one space. So it has to move multiple spaces. And so that's the rule for pickets, and whether you like it or hate it, that's exactly what it is. So, okay. And so here, basically the point is that what you have to do is you have to check to make sure that there's no attacking pickets. And so here's an example that if these were bishops, there would be attacking bishops, but there's no attacking pickets because this one can't move one space. It can't move here, it can actually move here, or say here, or here. Or no, I'm sorry, it can move here or here, but it can't move here or here, and it can't move here or here. So it's safe. And then this picket is also in a mutually non-attacking position, and this picket is also in a mutually non-attacking position because they're one apart. So when they're close to each other, they're in the mutually non-attacking position, and they can't move vertically or horizontally. It's not like a queen. So so these are safe and these are safe from that. Okay, and then this one is just totally right. Even if it were a bishop, it couldn't. There's nothing in its path. Right? Yeah, so pickets have a one-space pacifism of some sort. Yeah, it's kind of like that. And then here's an example where the bold ones can attack each other, right? Because they're two apart. And then here's another example where, so here, these two can attack each other, but then these two are not. These are kind of a knight's move apart, so they can't attack each other. These two are a knight's move apart, and by that I mean they're 2 over and 1 up, 2 over and 1 up, or 2 up and 1 over, or 2 over and whatever. So it's a 2 and 1 move. And so, because the pickets don't do knight's moves either, right? So, cool. And then here's an example of a bunch of them that can attack each other. So this one can attack this one can attack this one can attack both of those, obviously. This one can attack this one can attack this one. As it turns out, though, this one can't attack this one. That's the only pairing that actually isn't quite right. But, so, basically we want to return, okay, so what are we doing here? We're going to return true for any grid where the pickets can't attack each other, and we're going to return false for any grid where we find some pickets that are attacking each other. Alright, so you get a grid, and let's assume that that grid is, I guess it doesn't even matter really if it's, so what are we supposed to do? Let's copy paste the name of the function, Pickets problem. And so what we're going to do is we're going to search every position, and I think that what we had is if it's a picket, so the answer is that either it's a P or a space, or maybe it's empty, I forget. Let's check with the problem. Marked as P, otherwise it will be a space for printing reasons. Okay. Alright. So let's just define two constants, space equals space, picket equals P, right? Just to make ourselves happy. And then, what else are we going to do? Right, so what we're going to do now is we're going to say for I, or let's just say for x in, well actually, okay, for y in range len board, for x in range len board. And so what we're going to do is we're going to say if, right, the thing at board yx is equal to a picket, then we have to search, right? Then let's make a little helper function, right? So if check picket board xy, or let's say if not check picket, return false. Otherwise, we keep going, and of course you might say, well, what's check picket going to do? It's going to check the picket at xy to make sure that it's not, and then here we'll return true. All right, so that function is done, right? We'll scan over the board, and we'll just check every picket. So here, I didn't, oh, actually, no, I did kind of make it. It can be a square board, so I think I probably made them a square board for the exam problem. Oh, it's a rectangular grid. Okay, so it may not be square, but it's going to be at least rectangular. So you do have to have a different index, right? The length has to be of board 0 here, or at least board Y, right? Like that. All right. Okay, so now what are we going to do? So now what we're going to do is, if we find a picket, we'll check the picket. So we'll say for what's a good thing to do? Let's say, yeah, for I in range len board. So I'm having a little. The reason why I've stopped is that I'm trying to think of like the easiest possible way to go up and down and back and forth and all this stuff. So, you know what? Let's be uber lazy, right? Very, very lazy, and just do this: -1 times the length of the board up to the length of the board, like that. Okay. And so what we're going to do is we're going to check if board x plus I, y plus I is equal to picket, return false. And otherwise we're going to return true. And so this is going to check the diagonal, I think. And then what we have to do is we have to check the like anti-diagonal. So we also have to check the other direction. So if board x plus I, y minus I. I think that's how it would work. And so, oh, actually, this is the easier way to do it. Let's start at 2. And go up to the length of the board. So we'll do this, and then we'll do this, x minus I, y minus I, x plus I, y minus I, and then x minus I, y plus I. And so that'll get us the 4 different directions, okay? And the reason why we start at 2 is because we don't want to start at 0, because 0, when you put I is equal to 0 in for any of these, it's just going to return board xy, which we already know is a picket, because otherwise this check picket function wouldn't have been called. And so basically what I'm saying here, I guess maybe I should actually draw it out with some kind of thing here. Maybe I'll draw it a little bit, because it might be a little confusing as I've stated it here. So if you have a grid, let's say we have a grid. Let's stop coloring that red because that would be horrible looking. Let's make ourselves a grid, right? So this will be a chessboard, a real full-sized chessboard. Well, sure. Okay. And now let's put a picket somewhere. Let's put a picket here, right? Big P for picket. Okay, so then the thing is we have to check all of the squares that well, yeah, so we have to check what? We have to check this, we have to check that, we have to check, not this one, we have to check this one and this one. So let's color those green. And then let's color this one, not this one, this one, this one, this one. So what are the indices here? So if this is index 0, say 1, 2, 3, so this is index 3, comma 0, 1, 2, 3, 4. So this is index 3, 4, right? This is index 3, 4, and let's make this font much smaller, let's say 20. And so if that's index 3, 4, then we also have to check what are all the indices of all these things. So this is going to be index 4, 5. This is going to be index 5, 6, right? 5, 6, and then we're also going to have index 6, 7, right? Like this. So we're going to have index 6, comma 7. And so you notice how do you get to all these indices? What you do is you say, well, if I start at 3, 4, I add on 2 to both indices, so I'll get 3 plus 2, 4 plus 2. Or I'll add on 3 to both indices, 3 plus 3, 4 plus 3, and that's how I get to these indices. Okay, cool. And so now how do I get to these indices? Well, I have to add on to one of them, right? I have to add on to the second index, but I have to subtract off from the first index, so I have to do, here it's going to be something like, when we subtract 2, it'll be 1, 6, and then when we subtract 3, it's going to be 0, but we have to add to the other one. So basically this is the minus plus direction, right? So that's the minus plus direction. This is the plus direction. Please stop that. It's I really want you to just do this. And then here, we're gonna have the, what is it? We're going down and this way. Okay, please stop. Okay, there we are. And then, unfortunately, sometimes I think the program thinks that, oh, I've misdrawn them. These two aren't green. It would be, see, it's good that I did that. Okay, those are now lime green or whatever. So then here, this is going to be position, position, say, what is it, 5, 2. This will be position 6, 1. And this will be position 7, 0, right? And this is how you have to solve this kind of problem. You have to draw this out, and you have to think about the indices, and you have to do this. Like, there's no shortcut here, right? Like, you don't just immediately jump to the answer like I did, because, I jumped to the answer because I kind of know certain things, but, like, if you don't know those things, then make sure you write this out, right? And so then here you see, if I subtract off 1, 1, I'll get down to here. That's right. This would be minus minus. I think that was just a copy. See, it's hard to... There we go. Yep. Okay. So that's basically what you have to do for this. And then you'll see how I made this in code, right? Basically, here in the code, this is the plus direction. Here's the minus minus. Here's plus minus, and here's minus plus. Right? And I start at a distance of 2 so that I jump over that initial square, and I go up to the length of the board. Now that's actually an issue here because it's possible that we'll leave the board. So why don't we just say I think actually y is the first coordinate, and 0 is less than or equal to y is less than length of board 0, right? And then what we can do is we can say if all of these things. So we only execute these if statements if the thing is in range. If it's out of range, then we're off the board somewhere, like we've gone too far in one direction. We don't care. All right? So these are, you have to understand, this is why do we do this? It's basically, we're testing, what are we testing here? We're testing understanding of a 2D grid. And here we're testing the understanding of how to check if you're on a board, right, in range. Because this one should be X. Okay. Oh, wait a second. No. Okay, right. Actually, I think these should be YX, not XY. See? There's no end, really, to the screw-ups. Okay, there we go. Fixed. It's because I did a YX here. Okay. Oh, Lord. There. All better now. Okay, so now let's, it's a little bit hard to know how to test this function. Like, I guess what we could do here is we could say Pickets problem, like print Pickets problem on, and then here we could say Picket space, and then you could do something like this. You could say this, comma, and then we would have the next row be, say, space, and then the next row would be, say, picket, right? And so, yeah, this picket here should be able to attack this one here should be able to attack this one here, and this one can't. It can only go here and here. This one can only go here, so they shouldn't be able to attack anything. So hopefully this will return false. Cool. And then if we test this out on, say, this one where we replace this picket with a space, this should return true. Okay, so it returned false. So that's bad. Unless, of course, there's something that I'm not thinking about, but this one should always... So this one is attacking a space there. So why is that returning false? It should return true. It should get through everything. So let's print out the X and Y, or the Y and the X. I'm always screwing that up now. Okay. What's going on here? Oh. Well, no. If check picket is false, then it'll print XY, so it is returning false from here. So let's print. Alright, this is horrible that we have to do this. But at least you're seeing some debugging, right? Debugging is 99.9% of programming anyway, right? Like, writing code is nice, but debugging is where it's at. Wait a second. That's not even possible. Oh, because, stupid me, you can't do this. You have to, we have to check every single different one. Unfortunately, there's no, I thought that there was an easy way out to check the range conditions, but there's no easy way out to check these range conditions. You have to check them all individually because they're all different, right? Yeah, they're all different because here, okay, here we go. There we go, false and true. Nice. Okay, so yes. So here, what this means is that the 0, 0, 1 found the 2, 2, 1, and that's right. And then here, nothing found anything. Okay. All right. So, okay. So that's basically the Pickets problem. Did I? Yeah, I did. I guess it's. I guess you could say I forgot. Sure, I forgot. Yeah, I'm surprised because if you, oh, I guess, yeah, that could give us an out of range error. So it's good it didn't do that. So it could always. That's the thing is like this always could give you out of range errors if you're not careful. So, okay. All right. Oh Lord. Okay, so let's see here. So this last problem is, I called it jelly bean sort for no particular reason. You're basically going to be given like a list of random colors, or really it's just a list of random strings, but and so what you're going to have to do is you have to count them, and then you have to sort them like this. Okay? So basically, if there's only one blue, I want blue to be first in the list, and with one, if there's 2 yellows, I want yellow to be second. If there's 3 greens, I want green to be third. Like, I want you to sort the numbers after that. And so here, I do not want you to use dot sort for the problem. I want you to write a sorting algorithm, right? To either use bubble, insertion, selection, merge, or quick. And the reason why I want you to do that is so that you think through, because the thing is, you have to modify. So if I say jelly bean sort, list of beans, right? The reason why I'm making you do this is because you can't just copy and paste the sorting algorithm. You need to think through what you're going to have to return. So, oh, actually, I guess you could. Well, that's a shame. Why was x minus I in the if statement? I don't know. Which one? It matches whatever this is, right? X plus I, X plus I, X minus I, X minus I, X minus I, X minus I, X plus I, X plus I. And here's minus, plus, minus, plus. So they should all match. If they don't match, they're wrong. Okay. So what I'm going to do here is I'm going to do my standard trick. I'm just going to make a color dictionary, like color map. I'll call it color map. And then I'm going to say for color in list of beans, if color in color map, right? Then we're just going to do color map at color plus equals 1, else color map of color equals 1. Right, there we go. So this is just counting the number of this is just counting the number of jelly beans with any particular color. This is not sorting them at all, right? This is just counting them. Okay. So now we're gonna come up with a list to sort is going to be equal to, let's say, empty list, and so we're going to say for color in list of beans. We can say list to sort dot append. Let's append a little sublist color list of beans. Okay, so that'll give us the list that we have to sort. And now let's write a sorting algorithm. So, I mean, I put the colors first, didn't I? Yeah, I did that intentionally so that dot sort wouldn't work. So now we have to write the sorting algorithm itself, right? So the sorting algorithm itself is going to be something on the order of for I in range. This is just for counting. I mean, you don't have to do it this way. I mean, I'll say it this way. You don't have to do any of the problems this way. In fact, the vast majority of students probably didn't do the vast majority of my solutions, I would say. I think that's fair to say. Basically, this one is counting them, and this one is just putting them in a paired list. I mean, I guess technically you could even just do... Can you even just do list of color map? Maybe. I forget. So, is list of beans color... yeah. Yeah. Yeah, you see when I go this fast, it's very difficult not to have typos. But anyway, okay, so... what am I doing? I was just going to do bubble sort. Or maybe selection, so I don't know what I'm going to do. I guess I'm just going to do... yeah, I guess I'll do insertion sort. So while, say, j is equal to I, while j is bigger than or equal to 0, and let's say list to sort at j1 is less than, say, list to sort. Well, I think actually we need this to be bigger than, strictly bigger than 0 if I'm going to do it this way. List to sort j minus 1, 1, because we need this extra 1, because remember, everything in this list, it's a list of two things. It's the color and it's the element. So, and then what we'll do is we'll say, we'll swap them, so we'll say swap temp equals list to sort j, list to sort j equals list to sort j minus 1, list to sort j minus 1 equals swap temp, and then j minus equals 1, and that's insertion sort, right? And so then we'll return the list to sort, and that's that. So you can choose. So at this point, I just chose insertion sort, mainly because insertion sort, holy crap, insertion sort is short in terms of length, right? It's one of the shorter sorts. Oh my god, this is bad term. Insertion sort is short. I can't even say it. The shortest sort is insertion sort. It doesn't. I don't mean time-wise. I mean code length-wise, right? Like bubble sort, I think, is about the same length. Selection sort is about the same length, I guess. Yep. Okay. Well, I guess I kind of ran out of time. I don't have time to do the files and folders problem. Basically, the trick to the files and folders problem, if you look at it, my hint is that everything is a dictionary. Okay, you're not actually making any files. You're not actually doing any file reading or writing. What you're doing is you're making some fake stuff. And so because you're making all this fake stuff, you should actually, I promise you, everything is just secretly dictionaries. That's the point. Files, like a folder is just a dictionary with all the files and subdirectories in it. Everything is just a dictionary, okay? So that's the secret to that problem. So anyway, okay. So this is basically what your final is going to be like in terms of structure. The problems themselves may be slightly easier, or maybe if I make them badly, they'll be harder. Who knows, right? So, okay then. Good luck. I'll be around on Discord, but I think this is the end of CMSC 201, right? We're done now. You just have to finish up all your work and submit it, and then you get your grade and you get to move on. So I guess the only thing is that in the so this is the other thing I'd like to say is thanks everybody for watching the lectures and sticking through the course and all that stuff, and good luck in 202. Good luck next semester. I'll see you if you drop by my office, which is hidden back in the ITE building. So, all right. And I'll post these solutions up to the GitHub, so you know 100% that these problems are not going to be used on the final. But yep. So. Okay, let's commit it. And then we commit it, we push it, and I might even maybe I'll add the solution to the files and folders problem. I'll just do it after class or something tonight. All right, well, anyway, guys, as I say, I'll still be around on Discord. I'm not disappearing forever, but in terms of the course, you're done. Go home. All right, see you, everybody.